Hello everyone, welcome to the first of the three lectures on AC/AC controller. AC/AC controller is a device which changes either the magnitude or frequency of AC voltage. That is, with the help of AC/AC controller, our input is AC and the output is also AC as the name suggests. But the voltage of the output is different than the voltage of the input, and or the frequency of the output is different in the than the frequency of the input. That is, we can control both the frequency and magnitude using AC/AC controllers. Now, AC/AC voltage controller can be broadly classified into two types: the voltage controller and cycloconverter. The voltage controller is the controller where the magnitude is affected. That is the magnitude can be decreased, or that is the RMS value of the voltage can be decreased by controlling alpha or firing angle. Cycloconverter is the controller where the frequency can be changed. Both voltage controller can be three phase or single phase. Similarly, cycloconverter can also be both for single phase and three phase, but the output for both of them is single phase. Now, the first topic on voltage AC/AC controller is single phase AC/AC voltage controller. The diagram is almost similar to the one we had for half wave rectifier. Only in this case there is another switch T2 which is connected in opposite polarity in parallel to the original switch T1 available. So we can understand that the switch T1 will work in the positive cycle when current goes in this direction, and T2 will work in the negative cycle when current goes in the opposite direction. Here we can see this is the gate pulse we provided T1, and this is the gate pulse we provided T2. Before any gate pulse is provided, no current flows through it. As a result, the output voltage remains zero. When a gate pulse is provided, the current starts flowing for it, and the output voltage assumes the shape of the input voltage, and the output voltage automatically again turns to zero when the angle is pi, that is when the input voltage becomes zero. When the output voltage turns zero, the output current also turns zero, and the switch T1 gets switches off automatically, because the current through the switch T1 is below the holding current. Next, what happens is, in the negative cycle we provide pulse to T2. When we provide pulse to T2, same case happen, but just in a negative direction. So the difference between rectifier and voltage controller in this case is, the voltage controller has a part in the positive direction and also has a part in the negative direction. But in case of rectifiers, both the parts, the negative cycle and the positive cycles, both were in the positive direction. So as a result, we can see that the amount that we have in the positive direction is the same as that we have in a negative direction, so that they cancel each other out, and the output is pure AC. This is called AC/AC voltage control. This is why it is called AC/AC voltage controller. One thing needs to be noticed, that the output is purely AC only because the firing angle here is same as the firing angle here. If these firing angles were different, the output won't be purely AC and there will be a DC component involved, because the voltage, suppose this firing angle is lower and this firing angle is higher. If that happens, the voltage at the positive half cycle will be greater than the voltage at the negative half cycle, and as a result there will be a DC component involved. That is, it will not be balanced. Now we are considering for the case when the firing angle is alpha, both the positive and negative cycle. That is, if positive angle firing angle is alpha, it is very obvious for the negative cycle firing angle will be pi plus alpha. If that happens, RMS voltage is V out RMS is equal to root over 1 by T integration of alpha to alpha to pi Vm square sine theta d theta. Now two things are to be noted. What are the two things? Firstly, we are not calculating the average voltage. Why are we not calculating the average voltage? The voltage in the positive cycle cancels the voltage in the negative cycle, and as a result, through a period, the average voltage is zero. This plus cancels this minus, and average voltage becomes zero. In any case, we have already learned that for AC circuits, the average voltage is zero, and this is perfectly AC, so we don't need to calculate the AC circuit. Again, I'm saying the if the firing angle here was different than the firing angle here, then there will be an average voltage, and we will need to consider it. The next thing is sorry, here science theta. Next thing is this part of the if we see, this part of the circle is positive, this part of the circle is negative of negative. That is, the value of sine theta here is positive, the value of sine theta here is negative. But when we are considering sine square theta, both becomes positive because minus square is plus. So as a result, this the sine square of this portion will be equal to the sine square of this portion, only because here and here the firing angle are the same. So we can write this thing as, for a time period, we have 2 Vm square sine square theta, because the positive cycle sine square theta is positive, in the negative cycle 2 sine square theta is positive. So from that we get root over 2 pi, our time period is 2 pi, integration of Vm, we consider the Vm square is out, integration of alpha 2 pi sine square theta d theta. Now what we can do is we can multiply here 2 and we can divide here 2. From there we get root over Vm square by 2 pi. These two are cancelled. 2 sine square theta. Now we know cos 2 theta is equal to cos square theta minus sine square theta. From there we get sine square theta is equal to or here 1 minus 2 sine square theta. So we get 2 sine square theta is equal to 1 minus cos 2 theta. So we can write integration from alpha to pi 1 minus cos 2 theta d theta. We can modify as root over Vm square by 2 pi theta minus half sine theta alpha to pi. So we can modify it as Vm square by 2 pi. For theta we have pi minus alpha minus half sine 2 pi plus half sine alpha. Now we know sine 2 pi is equal to 0, so we'll get now we can consider Vm square by 2 pi. We can take this out and we'll get Vm by root over 2 pi root starts pi minus alpha plus half sine twice alpha. Here we have twice alpha, half sine twice alpha. So this is the expression of RMS voltage. It is to be noted that if alpha is equal to 0, we get this is equal to 0 and this is equal to 0, and ultimately we will get Vm by root 2, which is the RMS voltage of the whole AC converter. That is, changing the value of alpha, we can change the value of the RMS voltage, and we can actually, by changing the value of alpha, we can decrease the value of RMS voltage. One thing is to be noted that it is very clear that the alpha we are considering is same here and here. If these alphas are different, the calculation will be entirely different. The process will be same, but the results will be different. We know input power factor is equal to P out divided by V in I in. Now we know V in is equal to Vm by root 2 since input voltage is purely sinusoidal. I in is equal to I out is equal to V out by R. Because everything is in series, then V out by R becomes Vm divided by root over 2 pi R root over pi minus alpha plus half sine twice alpha. If that is the case, we get power factor is equal to, in the output we get V naught square divided by R. In the input we will get V input is equal to Vm by root 2 and I input is equal to uh, V naught by R. V naught divided by R. So and this can be modified as, sorry, here V naught square by R. Okay, this can be modified as V naught square by R becomes Vm square divided by 2 pi R pi minus alpha plus half sine twice alpha whole divided by Vm by root 2 into Vm by root 2 pi R root over pi minus alpha plus half sine twice alpha. If that is the case, this Vm and this Vm square gets cancelled. These two get cancelled with this 2 root 2, and these are also get cancelled. So what we have is this pi, we have this pi, this and these expressions. So it will become 1 by root over pi into root over pi minus alpha plus half sine twice alpha. It is to be noted that when alpha is equal to 0, it becomes 1 by root pi into root pi, that is input power factor becomes 1. So input power factor is maximum or the best when alpha is equal to 0. But when we increase the value of alpha to decrease the output voltage, we get the input power factor gets deteriorated. That is, the input power factor works best when the input power factor is the best when there is no when we are not using AC/AC controller. So we can use AC/AC voltage controller to get AC voltage output with a decreased magnitude, but we do this at the expense of deteriorating the power factor. There is always a trade-off involved. That's all for single phase AC/AC voltage controller. In the next lecture, we'll be learning about three phase AC/AC voltage controller. Thank you so much. If you have any queries, you can direct them to the discussion portion of Bugs platform.